Okay. So I can share the PowerPoint. Vedete tutto, sì. Okay. Now we should be ready. Is it okay from home? Can you see the presentation?
Sir.
No.
Yeah.
Okay. 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 Great.
Thank you.
Thank you.
All
Grazie.
right.
Okay. So we continue the discussion we started 2 days ago. Yes, on Tuesday. And at that time, we were considering what? A full wave rectifier with already a capacitive filtered output. And what we saw was that basically, if we consider the green line here as the input voltage, in this case, we neglect the resistance, the winding resistance, and also the diode resistance, but we have only the voltage drop due to the knee voltage, the V gamma of the diode. What we see is that basically the capacitor, and so also the resistor, has a voltage which is more or less following the input voltage. We see that at the beginning the capacitor is discharged, so it starts charging, then goes up to here. We have a peak voltage which is about 5 minus V gamma, so it's 4.3, 4.4. But then when the input voltage goes down, the diode opens, and so the capacitor cannot follow anymore the input green voltage. What happens is that the capacitor starts to discharge across the resistor here. Okay. Also, it's interesting to see that the peaks of the current, these are the peak current in the capacitor. They are basically induced when, here in this part, when the capacitor is starting to follow the input voltage. You see here? So that's the time when we have the peak current entering peak current in the capacitor. So we have a positive peak. While when the capacitor is discharging here, we have a negative current. You see the current is just below the 0 amps. So it is a negative current, meaning that the current is coming out of the capacitor and going to the resistor. What is interesting is that basically this current here can be considered almost constant, because the capacitor is large enough that the voltage variation is very small. And that is some kind of hypothesis that we are going to use in the next demonstration. Okay, but we can still see here. Actually, if we zoom a lot, we see that the current is negative, but is decreasing a bit. It's just going down a bit. It follows the voltage that is decreasing as well. But in average, this voltage is quite constant. Okay, so I can try to connect all those concepts in some formula. For doing this, okay, we are here. We consider again the previous drawing, and what we do is that we remove basically the blue line is the voltage after the diode if we don't have the capacitor, okay? Because we know that the input voltage is via node 1, that is not here in this graph, and it goes up to 5 volts. The blue graph instead is the voltage on the node 2 without capacitance, and the green line instead is the voltage with the capacitor. So basically it's the same as the blue line here. Sorry for changing the color, okay? Okay, so how can we define a number of definitions? basically, if we follow the green line here, we can see that we can define an average voltage that we call V barred or VDC with this red line. It is basically in between the two peaks, the maximum and the minimum of the green line. And then we can also define a ripple voltage between the maximum and the minimum, again, of the green line, okay? So we can consider that actually the total green line is given by the sum of the VDC plus the ripple voltage. And okay, here it says that the maximum voltage on the capacitor Vmax is actually given by the maximum input voltage minus 0.7, that is the knee voltage of the diode. Let me see the next picture. Okay, here it's a zoom, let's say, of what we saw before. So again, VDC means the average voltage in the output, the average of the green line. VR is the ripple voltage. But also, in this graph, I indicated the current through resistor R1. The current through resistor R1 is basically the same shape as the voltage across resistor R1. Due to the Ohm law, you just divide the voltage times by the resistance. And so you get the same shape. This current is a bit more than 40 milliamps, just because you use the 100 ohm resistor. If you divide 4 volts by 100, it makes 40 milliamps. And so we can say that we have, again, an average current that we can calculate as VDC divided by R1. I did not indicate here. We can also consider a current ripple if you want. But this is not important in this part of our talk. So I do not indicate this current ripple. On the bottom, we have IC1, that is, again, the current on the capacitor. And we see that there is a short time T1 during which the capacitor is charging. And basically, this is when the input voltage is higher than the capacitance voltage. So the capacitor tries to follow charges and tries to follow the input voltage. Then the diode opens, and so the capacitor is discharging through the resistor. And again, we see a negative current. And we call this time T2, this interval T2, the time during which the capacitor is discharging. Okay? Okay. 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 Just to, we can make a graphical consideration. You see here, there is a blue area. There is a blue area and a green area. The blue area is the area given by the integral of the negative current across the time T2. So I am integrating the negative current during T2. Okay. Then I am also integrating in the green line the current during time T1. And this is the green line. Due to the charge conservation, the charge that is entering the capacitor, the green line, zone, must be the same as the blue zone, okay? So the two integrals must be equal and opposite. So the total charge difference is 0 in one cycle, in one entire cycle, okay? And that's what we are going to use for trying to calculate the ripple voltage, VR, first. So now we are going to calculate how much is the ripple voltage, and then we try to calculate that ripple factor that we defined the last time, and that's reported here, okay? So there is a two-step calculation. Obviously, it will be something quite approximated, but the approximation is quite good for our purposes. How can we do that? Okay, so basically what we saw is that there is a charge conservation. So the integral during the peak is equal to the integral during the negative current. But if we want to calculate one of those two integrals, the green integral is much more complicated than the blue integral because we don't know the exact shape of the peak. It's a nonlinear behavior that is very complicated. While we can almost easily calculate the blue zone area because we can consider that we have a constant current, more or less, for a certain time interval, okay, T2. And here we do, so two hypotheses that we need for making an easy calculation of this integral. The first hypothesis is that if we have a C1 that is very large, we can actually consider that the output voltage is quite constant. There is a small ripple. Okay. If the capacitor is 0, we have the maximum ripple. We have no filtering. But if the capacitor is high, if the capacitor was infinite, we would have no ripple at all. So we have an adequate value for this capacitor C1, okay? And we have, anyway, we have some ripple. So the ripple is small that sometimes we can neglect, sometimes we want to just calculate the ripple, okay? So first hypothesis is that VO is constant with small ripple. The second hypothesis is that, just for making things easier, sorry, the time T1 tends to be very short, much shorter than time T2. This is true if we have a large capacitor. In this picture, I tried to enhance a bit the two intervals so we can see them separately, but in general, T1 is much, much smaller than T2. So we can actually say that T1 is negligible if compared with T2. This means that when I have to calculate T2, I can say that T2 is basically the time between two peaks. So I neglect T1, T1 is off, but what is the interval between two peaks? This is a double wave rectifier. So that means that if the input waveform is 50 Hertz, F0, here the peaks are 100 Hertz. That's why T2 is the half of the TO, which is the 50 Hertz period, okay? So I can write 1 over 2 F0, 1 over 100 Hertz. Okay, so this T2 is basically 10 milliseconds if you are working with the 50 Hertz. Okay? Was there anybody asking me something from home? I heard some. It's okay? Okay, in case, just call me. Okay, so this is the second hypothesis. When we have this T2, we can, instead of T2, put 1 over 2 F0. Okay. Now, we go back to the discussion we did before. I want to calculate. Prego, sì. Prego.
T0 in this case is
it's the period of the 50 years. 20 milliseconds. Okay.
Okay.
Your colleague was asking what is T0. T0 is 20 milliseconds because it's the reverse of 50 Hertz. Okay. Okay, sure. And so delta Q is the charge that we are losing or during the capacitor discharge or the charge that we are gaining when the capacitor is charging again. We know that we can write delta V equal delta Q over C1. So if we can calculate delta Q, we can calculate the delta V. Oh, that is the ripple voltage. That's what we are going to do. Okay, so now we must do the integral of the current during one of those two periods. I told you that it's easier to calculate during the discharge, because in this case, we must calculate the integral of IT, the T, over the T2 interval. But just because we saw that the current is constant, we can take the current out of the integral. It remains only the integral during T2. And so what we get is basically this IDC T2. That is the integral. Here we have still T2, but in a short while we will substitute T2 with the formula that we calculated before. Well, the IDC can be changed with, we wrote it here, VDC over R1. So we get this here, times T2. And when we want to calculate the ripple voltage, we divide the charge variation by C1. It's an approximated, a bit approximated calculation. What we get is VDC divided by R1 divided by C1, comes from before, times the T2, which is 1 over 2F0. Okay, so we get to this final formula. We can write it as, it's a bit approximated. Anyway, it's good enough. VDC divided by 2 times F0 times C1 times R1, or if we prefer, VDC divided by R1 is IDC. So we get IDC divided by 2F0 C1. We can use one of those two formulations to calculate in good approximation, which is the variation of the output voltage. That is the ripple voltage. Okay. So it's very, I like this demonstration. It's a simple demonstration, but just tells us how we can try to calculate complicated information in an easy way sometimes, if we are lucky. It doesn't go this way all the time, but it's good if we can use this. Okay, so now we know how much is the ripple. The problem is that now we must take the root mean square value of this ripple. Okay, and that's the bit more complicated part of it. Anyway, in most cases, we are more interested in the ripple than in the ripple factor. Because just the ripple tells us how much noise is in the output voltage. And the ripple voltage is one of those parameters that usually they give you in the data sheet for a power supply. So they tell you, okay, you turn on the power supply, you put a load resistance of something. In this moment, the system is giving 1 amp of current, for instance. Well, the output voltage will have an average voltage of 5 volts with a ripple of 100 millivolts, or 10 millivolts, or 1 volt. 1 volt is really bad. But 100 millivolts can be the typical ripple for a power supply like the one in the PC. I would not expect anything better than 100 millivolts. But anyway, now it depends on the equipment that you are supplying, powering, to understand if those 100 millivolts are okay or not. There are some equipment that cannot tolerate that much ripple. There are some equipments that can tolerate it. Just to have an idea, if I'm using a digital system, which is supplied at 5 volts, and I have a supply voltage with a ripple of 1 or 2 volts, that means that the voltage can go up to 7 and down to 3 volts. Apart from the peak peak voltage, but what is worse is that the 3 volts can be below or within the threshold, the band, where you don't know if an input to signal, digital signal, is 1 or 0. So this means that you can lose the information about the incoming bits because the voltage is going up and down too much. Okay, so probably you need a better filtration of the input voltage. Okay, so this is just a simple example to understand why some equipments are more or less tolerant to the input ripple. Okay, so now the point is that we want to calculate the root mean square value of this ondulation, of the V ripple. In this case, we must know the shape of the ripple voltage. If you look here, the shape is not quite easy because it's made by an exponential decrease plus a piece of, it's the top of a sinusoidal waveform. Okay, so you have a bit of sinusoidal waveform here when the voltage goes up, plus an exponential decrease in voltage. That is going to be too complicated to examine, but we can do a small approximation. Why? If the charge is very fast, so if T1 is short, we can approximate the sinusoidal waveform with an almost vertical line. Okay. Okay, then if the exponential is not very steep, it's quite flat, we can approximate this exponential line with a linear line. So we end up with a sawtooth waveform, something like this. Look at the green line. It's again quite approximated, but at least we know something. Otherwise, if we want to make the calculation by hand, it's very complicated to do that. You can do all the calculation if you are using a simulator, but at the moment we want to understand things, so we are doing the calculation by hand. Then we can use the simulator. The result will be precise, but we will lose a lot of information about what we are going to do, which has the parameter that we can change to improve the situation. Okay, so again, we have all the picture that I used before. And my approximation is that the green line will become something like this. That's the ripple. We have a voltage, a sawtooth, which we indented this second sawtooth, that goes up to plus VR divided by 2, goes down to minus VR divided by 2, and it lasts between minus and plus 1/2 of T2. Okay, so the whole waveform will last T2 that we already calculated. So basically, those are two pieces of a triangular waveform. If we take just the integral of this waveform here, so if the integral was over VR, we would get 0, because we have a positive part and a negative part. But we are interested in the square. So we have to take, what we are going to do is, we consider the square of the voltage, we integrate the square, and then we divide by the time. That is the root mean square, the average of the square of something over one cycle. Okay, so this means that when we take the square, we will get two positive areas. Okay, so when we take the integral of the square of this voltage, we will get two positive areas that are the same. So just because we want to do the smallest effort that we can, we just say, I calculate only one triangle, and then I multiply it by 2. So the integral will be between 0 and half T2. Okay, and then I multiply the result by 2. Okay. First of all, we need a formula. So we need an expression for this VR. The expression for VR is something like we have the VR over 2 in a time T2, half of T2, has a negative slope and is proportional to time. So the expression is basically a line passing through the 0 point with a negative slope. When, for instance, time is equal to T2, half of T2, we get that the voltage is minus half of VR, so it's correct. Okay, that's the correct formula for this line here. Now, we have to calculate the root mean square. As I told you, we'll take the square root of the average across the time T2, so 1 over T2, of 2 times the integral calculated between 0 and half of T2 of the square of this voltage. Okay? So, we try to have a look here, and we take off everything that we can. Basically, VR is the maximum, is a constant, is squared, and goes out of the integral. T2 is again a constant, is squared, goes out of the integral, but it's elevated to the third power because 1T1 was already there. So we have to calculate the integral between 0 and half of T2, the square of time. Which means, if we can remember it, 1/3 of the cube of T. Okay? Which has to be, that's the primitive. We have to calculate between T2 half over 2 and 0. The 0 gives 0, so we only have the cube of 2 over 2 at the third power, 2/3 which comes from here, and what is coming from before. The calculation should be right, okay? So you can simplify everything, and you will end up with 2 goes out to the second power, VR goes out, but we have only the square root of 3. So basically that's the root mean square value of this ripple. VR divided by 2 times square root of 3.
And this is the area of the...
This is the average of the area of the square of the voltage. Is correct? Something like that, okay, more or less, okay. Because we took just the average, and then we calculated the square root of everything, okay. This is the equivalent of the effective voltage. Basically, the definition of effective voltage is this one. Instead of calculating it for a sinusoidal voltage, we are calculating it for a sawtooth, okay? Okay, now we can take all the different parts. And so we have the root mean square, we want to calculate the ripple factor. The root mean square of VR, we copy it, and we have to divide by the average of the output voltage, VDC. So what? VDC, we took the ripple, okay. We had to copy the formula of the ripple from the previous slide, so it's this part here. So we copy the formula of the ripple, it's this part here. Then we have 1 over 2 square root of 3, that is this part here. Then we are dividing by VDC. So simplifying everything, we get 1 over 4 times square root of 3, F0, C1, R1. Okay. Again, what we see in this formula, that is more or less is similar for some instances to the previous one, to this one. What we see here is that the ripple factor, or more in general, the ripple, is a reverse function of frequency, capacitance, and load. So, if we want to reach a particular ripple factor, for instance, we realize that in our equipment, the ripple factor is too high. There are many ways that we can reduce the ripple factor. One is to change the frequency. Can we do that? It depends. If you are taking the power from the mains, we cannot change the frequency. But if we are designing a switching power supply, like what we will do with Professor Vitale, you can decide to increase the frequency. If you increase the frequency, the ripple will go down. Okay? We can increase C1. Prego. Okay, that's a problem. So your colleague is saying if you increase the frequency, we have more problems with electromagnetic interferences. Yes, that's a big problem, but we are engineers, and so we know that our life is a trade-off between many things. Okay, we must accept the compromises. There are sometimes when we can do that. For instance, if we are interested in having a good ripple with a small packaging, if we increase the frequency, we can also decrease the capacitance. So this means that the equipment will be smaller, the power supply, because the capacitor is one of the biggest parts of our power supply. When you will study the switching power supply, you'll see that there are 2 big components. One is the capacitor, the other one is the inductor. If you increase the frequency, they are both going down. So the modern power supplies are working at high frequencies. So everything can go down, can be smaller. Obviously, the problem of electromagnetic interference becomes worse. That's for sure. Okay. Well, the last solution is just to remove the load. Okay, because if you increase to infinite the load, okay, there will be no ripple, but that's not our purpose. We want to give some power to the load, so it's not something that we can change, okay, for sure. Okay, if are there any question about this part, then otherwise I move. Anything from home, I want to see. Anybody complaining from home? Not at the moment. We are 16, 25 from home and a number of people from
Teacher,
here. Okay.
sorry,
Prego, prego. Please go ahead.
I speak English or Italian?
Yeah, okay.
Ok, allora
so-
l'ultima parte non l'ho capito. L'ultima parte non l'ho capito molto bene per il calcolo, diciamo, del root mean square, per il calcolo della frequenza.
Quale parte? Scusi, dice, non ho capito bene questo RMS.
L'ultima
Quale
parte
parte?
l'ultima parte
Sì.
che lei ha spiegato adesso, cioè nel senso riguardante la frequenza per il calcolo del root mean square, quest'ultima parte non l'ho capita molto bene.
Questa formula sotto.
Sì, esatto.
Okay, no. Your colleague did not like my comments on this part of the formula. Okay, I'll try to repeat it again. Okay, so basically, once we have calculated the ripple factor, that is this final formula here. Okay, so the formula is okay for you. La formula va bene, no? Come calcolo?
Yeah, sì,
Okay.
sì, va bene.
Okay. Now, what I was saying is that if we consider the ripple factor, that is this formula here, or also, if you consider only this part here, this is the amplitude of the ripple voltage, okay? What we see from here is that if we want to try to reduce the ripple factor, so to reduce the ripple, we can either increase the frequency, if it is possible, or increase the capacitor, or both of them. So because if you increase the frequency of the capacitance, the ripple will go down. I don't say that we can increase the resistance, because increasing the resistance means basically that the load is disconnected. So it is no meaning. Why should we disconnect the load that needs power? Okay. So those are the two ways to reduce the ripple factor. Sometimes we cannot change the frequency, as when we are using the supply from the mains, from the wall. So the only strategy that we have is to try to increase the capacitor. Va bene così? Is okay for you now?
Yes, I'm okay, I understand now.
Okay. Well, so these are a number of calculations that are useful for defining, let's say, a simple power supply. Basically, what we are talking about was a simple power supply using only a transformer, diodes, and capacitor. Okay, we calculated the ripple, and maybe this ripple is too much for us. Okay, we could increase the capacitor, but if we increase the capacitor, increasing the capacitor means that we need a bigger capacitor, which is large, is big, but is also expensive. So maybe this is not the best solution if you want to get a better ripple. The different solution could be that we add some electronics after the filter, the capacitor. If we choose, we design the correct electronics, maybe implementing a piece of electronics, an electronic circuit, will be cheaper and smaller than increasing the capacitor. Okay. So now we are going to study what we call the stabilized power supplies. Stabilizzati power supplies. Okay. Basically, what is a stabilized power supply? It's a feedback system where we compare in real time the output voltage of our power supply with the reference voltage. If the two voltages are okay, are the same, no problem. But if there is a difference between the output voltage and the reference voltage, the system will change something in order to keep the output voltage as constant as possible. When we say reference voltage, I mean something which gives me a voltage absolutely stable. So far, we have not seen anything which can give us a stable voltage, because here we saw ripple and so on. So what I'm going to study now is the possibility to create some circuits called voltage references, which give us a stable reference of voltage. once we create this kind of circuits, we can include these circuits in a feedback system. So the final part of this consideration will be studying what a stabilized power system is. Is a feedback system which has within a reference voltage. So you can compare the output voltage with the reference voltage. So it's better if first we study the reference voltage circuit and then we move to the stabilized power supply. And that's what I'm going to do now. So we are going to use stabilized power supplies. We are going to define stabilized power supplies, okay? In theory, if we know how to do it, the simplest way to have a stabilized power supply is this picture here. We have basically a VCC, which is a voltage source. This voltage source can be a battery, but can be also a circuit like this. So mains, transformer, diodes, capacitor. We don't have, in this case, the resistance R1, because the resistance R1 means the load. But in our case, the load will be all that circuit here. Okay? So in this schematic here, I say that I can tolerate a VCC with some ripple, but then I want to have an output voltage which must be absolutely stable. How can I do that? Well, first, I use the VCC to supply to power a voltage reference circuit. Okay? So now my problem is how can I get a very stable voltage even if it is supplied, powered by an unstable voltage. That's our first step. Then we have a second step. We will see that the reference voltage circuits are okay. We are able to do them very good, but we cannot take current from those references because they are very delicate circuits. So if I want to get a lot of power, of current at a certain voltage, I need a buffer. What is a buffer? A buffer basically is a circuit that has a high impedance at the input, so that the voltage reference circuit will not be loaded and will be very stable. But then this buffer has at the input inside some power electronics that is able to supply a very strong current, keeping the right voltage. If you see here, I summarize it like an op-amp, operational amplifier, power operational amplifier, that simply compares the output voltage with the reference voltage. But it is able to give a lot of current. Op-amp. Operational amplifier. Sorry. My lips were a bit like this. Okay. Dry. Okay. So buffer basically is what we call a voltage follower.
I think power.
Yes, is a power operational amplifier. Okay. Power means basically that the difference with a standard small signal operational amplifier is that after the operational amplifier block, we have a power follower. It basically is a push-pull system with power transistors. Okay, so it's class B amplifier, basically, following the button. But everything can be inside this. So one way to have a stabilized power supply is to use this strategy. Actually, we can do it in this way, but probably we will see in the future a combination, a simple circuit, which tries to optimize the number of transistors. So it's the total function is like this, but actually is a simplified version of what we could do in this way. Okay. Okay, let's go back to the reference voltage, because from now on we will talk about, and probably, yes, I think at least the whole day, we'll talk about the reference voltage. I don't know even if we can finish today or tomorrow. Anyway, what would we expect as a reference voltage? For me, a reference voltage is a voltage generator, this one, which gives a voltage not depending on VCC and temperature. Actually, here I wrote that this voltage reference in a real situation can depend on the VCC and on the temperature, on the junction. This is a TJ, junction, sorry, in the temperature of the device, okay? What we want to do to get is some system where the dependence on the VCC and on TJ is almost zero. But in general, we will have a dependence on this, okay? We will see what happens. As I told you, usually I am able to do very stable system, but this stable system have are real generator, voltage generator, so they come with an output resistance here. So in total, this reference voltage block here has a dependence on VCC, the temperature, and the current coming out. Because if there is some current coming out, we have a voltage drop across the output resistance, and so we have again a variation of the voltage reference. Okay, so what I told you, one way to neglect the dependence on the current is simply to connect the voltage reference to a high input, to high resistance input circuit, like the buffer here. Okay. If we don't take any current from the voltage reference, so the next stage is a high impedance amplifier, we don't have this problem with the current. Sì. Sì, sì. VCC, sì, no, okay, there is a node missing here, okay. Let me see what your colleague was saying, that I forgot to put a node here. This is a node. But actually, I took the picture from from a data sheet, so it was not my fault. It was their mistake that they forgot. Okay. No. Okay. Anyway, yes or not? No. I have to take it off. Sorry again. Because otherwise, it looks like there's a big short circuit here. So it's better if you don't. We should improve a bit the system, okay? Well, let me take it off. Otherwise, someone will tell me that there is a short circuit between VCC and this, okay? So it's better if I take it off. Then at home, I will try to clean it up a bit. Can I do that now? Schermo nostro, gomma, rubber. Okay, let me take this off, okay? Then I'll adjust in a different way. Basically, what we say is that there is some VCC going inside this box. There is a ground for the system, but the equivalent voltage generator is connected between ground and the output. Okay, so as I told you, if you want to solve the problem about the output current, we just don't take any current. Anyway, in the next consideration that we will do, we will consider the whole dependence of this reference voltage also on the current, temperature, and VCC. So we write the complete formula, and then we can decide what we should change to improve the things, okay? So at the end, we'll try to remove the dependence on the current as well. Now we must decide how to do this block here. I will show you that we have different circuits starting from the easiest and going to something more complicated. Well, the easiest way to have a voltage reference is something that you already know, the Zener diode. Old, good Zener diode. The simple Zener diode. It's simple. And what is the easiest way to use a Zener diode? Simply, we put a resistance on top of the Zener diode. We put a VCC between the resistance and the ground, and then we take the voltage across the Zener diode. That's the easiest way to have a reference voltage. Do you remember that the Zener diode were particular diodes which were operated in reverse bias, and they used some braking phenomenon so that, okay, that's the typical characteristic of a Zener diode. If the Zener diode actually can be used also in a direct way. If we have a direct biasing of the diode, we are working here in the first quadrant. Okay? We put a positive voltage, and we have a positive current. Actually, here is a bit expanded, but we could say that there is a 0.6 volt knee, and after 0.6 volt knee, the current starts to increase. In this case, the picture is very zoomed, so actually this shape here is an exponential, if you remember. Okay. But we are going to use a Zener diode in this part, in reverse biasing. Okay. So what happens is that if we increase the reverse bias up to a certain voltage, the current is almost zero. After we overtake the VZ0 like this, there is an abrupt increase in the reverse current. So that's where we say that the diode is in breakdown zone, is going to operate. The diode can be operated in this dangerous zone only if we can limit the current. Because you have to remember that if we have a certain voltage across the diode and there is a certain current, the diode at that moment, for instance, consider these lines here, VZT and IZT here. That's a possible biasing point for the diode. In this case, the power that is dissipated across the diode, in the diode itself, is equal to the product IZT times VZT. So if you consider the area of this box, that represents the power dissipated by the diode. As you can see here, if I just increase by a little bit the reverse bias, the power will increase enormously. So the Zener diodes are very delicate because after we go over the breakdown voltage, a small variation of the breakdown voltage will increase enormously the area, and so the power dissipated in the diode. Usually when we buy a diode, we ask for a diode of a quarter watt, half a watt, 1 watt. That's the maximum dissipation that the diode can tolerate. Okay? So one of the specifications for a diode is the maximum power that can be tolerated, apart from the reverse breakdown voltage. How can we limit the current? One way to limit the current is to put the resistance in series. So now we can, basically when we put the resistance in series, if you remember, we can draw an operating line, load line, so-called the load, la linea di carico, la retta di carico. The load line that, if you remember, can be calculated just connecting the point VCC, in this case it's minus VCC because the diode is reverse biased, with the current VCC over R. That would be the current if the diode was a short circuit. Okay, so if we put 0 voltage here, the maximum current through the resistance is minus VCC over R. We connect this line, and so it means that for this diode, the operating point is here. Then set intersection between the characteristic of the diode and the load line. Load line, la linea di carico, la retta di carico, load line. What we see here, for instance, is that now we can control much better the current through the diode. Because if we want to increase the current, we must increase VCC. But we must increase a lot of VCC for increasing the current. While if we just we tried to control the voltage, the current with a pure diode only, it was a very delicate situation. A small increase of voltage would increase a lot the current. So that's why we usually place a resistance in series of the diode. So we need the large variation of VCC for changing the voltage. Something that I would like to say, usually in the data sheet you can find that the VZ0, this represents basically the voltage at which we have a breakdown voltage. Then the manufacturer will suggest us that probably the best place to operate the diode is around here. You see EZ test and VZ test. So that's a safer point. Safer, I mean, it's a more stable point. Why? Because on this point here, we have basically a variation of the voltage, a slope that is already constant. This means that, for instance, if we work here on VZ at 0, we can have some variation of the voltage and of the current, and the voltage will change a lot. While if we are here in VZT, we can change a lot the current of the diode without having large change in the voltage. Just because the slope of this area here is very high. This means a dynamic resistance, Rz, that is very small. What we usually do once we work on this part is to change the Zener diode with its equivalent model in this area. We can approximate the equivalent model for the Zener diode with these two components here. Basically, VBZ is VZ at 0, more or less, plus a dynamic resistance that here is indicated as Z at Z, sometimes they say Z at Z, which means RZ, okay, it's the same. I'm taking this picture from the Serra Smith and this picture from the datasheet, so sorry for the different letters, okay, lettering, but they're basically the same. So in our model, we can model this when the diode is in breakdown with those two voltages, VBZ and Z at Z. That is the dynamic resistance. This means that if we have no current, so basically here, with very small current, we will see across the diode only VZ0, this value here. When we increase the current, there is a voltage drop given by the slope here, and so there is a small increase in the voltage of the diode. The higher the current, the higher the voltage across the diode, okay? So from now on, we will study this circuit here, which contains already the model for the diode in breakdown zone. And so we can do all the consideration on this model. Okay, before we go further on, I would like to do some consideration about the Zener diode. You already studied Zener diode in electronic devices, subjects like those. Here I want to remember only some things that are useful for our purposes, okay? So I'll just say a few words. The few words that I'm going to say are related to the variation of this VBZ with temperature. Because this graph here, this plot, is valid only at the room temperature. But what is it going to happen if we change the temperature? Because the room temperature has changed, or because the diode is heating itself. That's another big problem. If the diode is heating itself, the voltage will change. That's why when we buy a diode, we say, I want a half-watt diode. The half-watt diode, half-watt, mezzowatt, diodo half-watt, quarter-watt, 1 watt, 5 watts, and so on. That is the maximum power that the diode can tolerate without destroying, but also without heating too much. If the diode is working with a high power and is small, it will increase the temperature of the junction. So it will give some error. While a big diode will have very big wires which can dissipate the power to the PCB, to the stampado. Okay. So everything has been calculated in the right way. Okay, so now, what is the behavior of a diode with temperature? Just to remember something, when we studied the PN junction diode, silicon PN junction diode, or the base emitter junction of a transistor, we studied somewhere that direct voltage will be reduced by 2.2 millivolts per Celsius degree. And that is valid for direct polarization biasing and for the PN junction of a transistor. Those are two concepts that we must remember in what we are going to say now. Those are for direct biased PN junction. But here we have Zener diodes that are working in a different way. They are based, let's say, on avalanche phenomenon, but it's not true, 100% true. If you look here, I wrote that actually there are different kinds of diodes. If the diode have a high breakdown voltage, when I say high, I mean over 5 volts, they will probably work on the avalanche effect. The avalanche effect is an effect where we have the charge that are energized by voltage gradient across the junction, blah, 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 all those stuff. And basically what happens is that for avalanche diode, we have a positive thermal coefficient. So if the temperature increases, the voltage will increase. The breakdown voltage will increase. While Zener diode with a threshold breakdown voltage below 5 volts are usually based on the tunnel effect. You have what is tunnel effect? You have the junction, which has been shifted due to the reverse bias. If you make the junction with high doping, you will have a very steep band. Steep bands means that the band gap will shrink so much that a charge can tunnel through it. It's close to the, was the de Broglie wavelength, something like that. So the distance is, between the band is so short that is below, is comparable to the wavelength associated to the wave associated to the electron, and so it can tunnel through the junction, okay? So it's not an avalanche, but it's tunneling. And so that's why, abbastanza, sì. In general, it's quite, all the diodes are the same. Let's do this, okay? So you're using the same phenomenon. If you want a high breakdown voltage, they use avalanche. So because you have a very high voltage gradient across the junction. If you want a Zener diode breaking at a low voltage, the only way is to increase the doping and get the tunnel effect. Then there are small differences between different families of diodes, but just because the doping is different. So you take the data sheet, and what you will see more or less is that for a 5-volt diode, well, a 5-volt diode is working in both ways. So you have a positive and negative coefficient that goes to 0, and we are lucky. So with 5 volts, more or less, we have a 0 voltage variation with the temperature. Then the higher the breakdown voltage, the higher the variation. For instance, around 6.2 volts, we have a plus 2.2 millivolts per Celsius degree. That's a magic number. While if we are around 3.3 volts, we have a minus 2.2 millivolts per Celsius degree. This means that we can match those diodes with transistors in some particular situations. Depending if we want to compensate a plus or minus, we can choose one diode or the other one. That's why I'm emphasizing these 3 voltages. Depending on the circuit we are interested in, we can change the diode. Obviously, we improve the stability, but we are losing what? The freedom of choosing the voltage. So every time it's a compromise again. Okay. For instance, in a circuit like this, where we have nothing to do with we cannot protect ourselves against the variation in temperature, the best choice would be to work with a 5-volt Zener diode. So it's already stable. But we are stuck with 5 volts. If we want a different voltage, we must change something else, okay? At least it is thermally stable. Okay, then we'll come again to this point. Okay, so basically, yes, I spoke about the thermal coefficient. That's the definition. So basically, is the dependence of the breakdown voltage only on the temperature of the junction, because obviously the breakdown voltage can depend on many factors. So that's why I'm using the partial derivative. We are considering only the relation of the breakdown voltage on the temperature. Okay, I hope I said most of these things. Okay. Now I want to improve, to derive some information from this model here. So I move to the next slide. What is my point? My circuit is like this. You have the VCC, the biasing resistor R, then that's the model for the diode, ZZ and the breakdown voltage, and that's the output. I'm considering the possibility to take some current from this circuit. Okay. Now I want to discover a relationship that links the output voltage VZ, we call it VZ, or sometimes we call it the V reference, both ways. And I want to link this voltage to the many parameters that are in that circuit, which can give us problems. If you remember, I said that this reference voltage will depend on the VCC, on the temperature, and on the output current. So I want to see if I can find a single expression which contains all those points. And so what I do is basically to write the output voltage VZ. This voltage VZ, once I indicated the three currents, we have a current coming from the power supply, VCC, I. IZ is the current which is going through the zener diode, and L is the current through the load. Cosa? Se fosse? No, this is just a simple reference voltage without any feedback, no problem. Okay, that's zener diode and resistance, nothing else. So once I define this current, it's easier for me to do the calculation, because I can say that the output voltage, VZ, is equal to VBZ plus the voltage drop across the resistance ZZ, which is IZZZ. Okay. Now, I leave there VBZ, and I calculate what IZ is. IZ is the difference between I, current I, and IL. But current I can be calculated, again, introducing my output variable VZ. So can be calculated as VCC minus VZ divided by R. And that's what I wrote here. So we have this current high, as this part here, which is VCC minus VZ, that is the output voltage, divided by R, minus the current which will go through the load, IL. All this part here is the IZ, the current going to the diode. Okay. Basically, I introduced the same output variable here and here. Now I collect the different parts. So if you see the second line, second equation is basically, here we have VZ. Here VZ is multiplied by minus ZZR over R. So if I take this ZZ over R minus and bring it on the first term, it becomes plus ZZ over R times VZ. Okay. So I am collecting this part here. What is left on the right term, on the right side? VBZ is here. The product ZZ over R times VCC, and it's here. And then we have ZZ IL, so minus IL ZZ. Okay. If I want to solve the equation with reference to in VZ, that is the output voltage, I must divide the right terms by 1 plus ZZ over R. That means just multiplying the right terms by the reverse of this. And that's what I did. So I took the reverse of this parenthesis, and so I have R over R times 1 makes R plus ZZ times all this part here. Last step is just to do the multiplication. So we get VBZ times R over R plus ZZ, this times this. Then we have ZZ that multiplies this part here. So what is left is ZZ over R plus ZZ. And then I have IL that multiplies ZZ times R over R plus ZZ. Okay, simply calculation. Well, actually, the last term is the parallel of two resistances. No, product divided by the sum is the parallel. So this is something that I can remember for later. Well, in this formula, I have the output. I will calculate the output voltage just considering the parameter that are in my system. Okay, so I know which is the breakdown voltage for the Zener diode. I know what is its dynamic resistance, ZZ. And I know what is the voltage, the power supply voltage here, VCC, and I know what is the load current. Okay, so if I know what is the load current, I have this term here. So actually, this is a function where the output voltage VZ is a function of VCC, of IL, and of TJ, because TJ changes VBZ. So inside VBZ, we have the temperature. So I basically got the formula that I was looking for. Now that I have this complete formula, I can do two things. I can calculate the output voltage once I know the single terms. That's interesting. But I also can do something more. In this case, I'm not interested only in knowing which is the output voltage, but I want to know what are the voltage variations with different terms. Just because we have a function, Vz, that is a composite function of many variables, a function with many variables, I can consider the partial derivative of this function on different variables, okay? So for instance, if I want to know what is the variation of the output voltage when I change the VCC, why am I interested in this? Because as I told you, the VCC is not a perfect constant voltage, but maybe a voltage with some ripple. So what I want to know is, if the input voltage VCC has some ripple, how much ripple am I going to find in the output voltage? Because I want zero ripple. So what I do is to do the partial derivative of VCC as a function of, Vz as a function of VCC. Okay. What I indicated here is what they call the stability factors. The stability factor are just those derivatives, because they tell me, just a moment, there's Professor Busak calling me, I don't know what he wants. Just one moment, please. Pronto, Alessandro? Ale? It's closed. I'm back. Next time. Okay, so I was saying, this stability factor are a reference. They tell me how stable is this function depending on one of the possible inputs. Okay, so if I change the voltage VCC, how stable is the output voltage due to the variation in the input voltage? I take the derivative of this second term here. Well, I have to take the derivative of the whole function. Just have to derive it according to the variable VCC. And what I see is that I get 0 from here, but only the coefficient, this coefficient here, is left doing the derivative. Okay, so I get ZZ divided by R plus ZZ. And that represents how much variation I have in VZ depending on VCC variations. How much, what is the ratio between the variation of the output when I have variation in the input? Okay. What I would like to have is a zero coefficient here. That means that any variation in the VCC will not give me any variation in the VZ. That will be the ideal situation. How can I do that? If I look at the formula, I see that if I increase R, this number will go down. Okay? So the higher is R, the resistance, the smaller will be the variation of the output due to the variation in the input. But if I increase R, what I'm going to do is decrease. If I increase R, this point will go down. So I will decrease the current in the Zener diode. And if I increase too much R, maybe I will go below the threshold. So ideally, I would like to have an infinite R, but I cannot do that. Because if I increase R and then I still want to increase the current, I must increase the VCC. So I need to increase the VCC to keep a determinate value of current that I like in the Zener diode. This means also, I didn't tell him anything, okay, sorry. This means also that, that's why I don't like informatics. That means also that I have to increase the VCC, but also that I have to increase the dissipation in the resistance R. Because if I increase the VCC, but the output voltage must to remain more or less the same, I will increase a lot the dissipation power dissipated in the resistance R. So ideally, I would like to have a very high resistance, but I cannot do that. I cannot increase the resistance too much, unless I remember something. When we were young, we studied some particular circuits which had a very high dynamic resistance. Because now, in that formula, actually, just because I did the derivative, I am more interested in dynamic equivalent resistance R than in the real value of R. If instead of placing a resistor here, I put here a current generator with a very high dynamic resistance, when the current generator will give me the correct biasing current for biasing the diode. But when I'm interested in variation of the voltage, I'm studying the circuit in a dynamic range. So in the dynamic range, the current generator will be open. There will be left only its parasitic dynamic resistance that I can do as I want. Remember current mirror circuits. In this case, if I use a current mirror circuit, a current generator with a high dynamic resistance, this value will go up to infinite, and the sensitivity will go to 0. So the first trick, if I want to get a very stable output voltage, which does not depend on the supply voltage, is to use instead of R, a current generator. Current generator. Okay, that is made electronically with a current mirror circuit. Okay. So that's the first thing that. So let's say we know how to solve this problem. At the moment we have not solved it, we still have R, but we know how to solve. We need at least 2 transistors, but we can know how to do that. Portato R goes to infinite, almost infinite. That's the dynamic output resistance of the current mirror, and so this number is decreased enormously. Just for an example, usually if I want to bias a diode like this, maybe R will be smaller than 1 kilo ohm. Probably will be 300, 500 ohms, something like that. If I put here a current mirror, R will go up to 100 kilo ohms. So I'm changing enormously the value of R, and so the system becomes very stable. Now we must go to the second step. The second step is considering the variation of VZ on the breakdown voltage. Here we are really in troubles, because if we optimized the previous step, increasing R, the value of R, when we increase the value of R also here, because it's the same R, these terms will tend to 1. If R is very big, the limit of this formula here for R going to infinite is 1. 1 means that all the variation of the breakdown voltage will be reported in the output. So I optimized the previous step, but I get the worst possible on the second step. All the variation in VBZ will go straight to the output voltage. But we know that if we choose a 5-volt diode, we will have a null variation in the breakdown voltage. So the only chance to get a good result here is to choose a 5-volt diode. If you don't choose a 5-volt diode, we must tolerate some variation in the breakdown voltage. Okay? That's not it. Okay, I was saying that in this, if we consider this term here, given that we decided to have a very high R in the previous step here, if R becomes very high, much larger than ZZ, this term, the whole term, will tend to 1. And 1 means that the ratio between the output and the input voltage variation due to the thermal variation is 1. So all the variation in the breakdown voltage will go straight to the output voltage. The only way to improve the situation is to use a diode which has 0 voltage variation with temperature. That is a 5-volt diode, Zener diode. Okay. There is not much that we can do. E voi eravate primi? Vabbè, presenza. Vabbè, quando prima di scappare vi facciamo l'appello. Ok. No, pensavo fosse già stato qualche altro professore prima di me. No. Ah, ok, quindi la famosa cross-contaminazione. Quindi, ok, per favore allora, quando finisco non scappate subito, ok? Aspettate 30 secondi così, ok? Ok, sorry, grazie. Okay. Okay, so the last step is this one. It has to do with the variation of the output voltage when we change the current that we drain from our reference supply. What we see here is basically this formula here represents the parallel between R and ZZ. So this resistance. We increase the R. If R becomes very high and we have the parallel of two resistance, basically what we see is the second resistance. So this sensitivity factor will be basically ZZ. But what are we talking about? This sensitivity factor, that is the ratio between the variation of the output voltage when the output current changes, is nothing else than the output equivalent resistance of this power supply. The whole circuit can be seen as an equivalent real voltage generator with amplitude Vz, but having in series a resistor which is given by delta Vz divided delta IL. Just consider this. If I want to calculate the output, the resistance seen by this gate here, how can we calculate the resistance seen from this port, from this gate here? We just put a test generator on this side. We switch off this independent generator, this and that. And what we see from here is just the parallel of the two resistances. One is going down here, the other one, VCC must be 0, so it's a gain. So basically, what this stability factor of the current as a function of the, sorry, the voltage, output voltage as a function of current is nothing more else that the output equivalent resistance of this voltage source here. R went up to infinite. Prego. Pardon? Anche in italiano. No, prego. Sì. Questo. Okay, yes, that's true, because I forgot the minus. Okay, no, you're right. So that's the, say, the modulus, okay, the absolute value. But you're right. Actually, now your colleague is saying that actually it's more correct to write here minus. I'll put it here at the moment, so it's easier. This minus means what? Basically, it means that when the current is increasing, the output voltage is going down. Okay, so the minus is correct. Okay, yes, yes. Okay, the resistance is positive because the resistance is a real resistor. But actually, when the current goes up, this is something which brings me into crisis. I don't know what to Okay, yeah, the resistance is a positive for sure. But the sensitivity is negative. Okay, yeah, it's minus, that's correct. So basically, when we increase the current, the voltage will go down. That's right. So what can we do? Okay, we said that the resistance R will go up. What is left for sure is the dynamic resistance of the diode. And we cannot do anything about this. When we buy one diode, the dynamic resistance that we'll see will be the dynamic resistance of the diode. So once we buy a diode, that we cannot change it. The only way to reduce the dependence of the output voltage from the current is to decide that we don't take any current from this voltage generator. How can we take no current from the current generator? Simply because we take only the voltage if the circuit which comes after this is a buffer with an infinite input resistance. So that's why in the previous slide I said I need a buffer. It's a very delicate circuit, and if you don't want voltage variation due to the current, we simply don't take any current. We could say, or we take a constant current, but that's more complicated. The best way is just we don't take any current. Okay. What time is it? Oh. Okay. I can try. Devo fare. Cosa sta? No, non posso prendere. Okay, sì, okay, they were asking here to just take 5 minutes rest. Okay, so I'll stop now and we'll be back in 5 minutes for the last 20 minutes of lesson. Okay. Just some minutes.
microphone.
Hello. We have only 10 minutes left, but there were a lot of problems with authentication for our colleagues here. Are you still connected or no?
Yes.
Okay, sorry for this delay. Okay, so in the last 10 minutes, what can we say? Okay, so I think we went through most of this slide. Okay, so we can examine a slightly different circuit. What is this? Basically, what we saw, if we go back to the previous slide, is that one way to have a stable output voltage, not depending on the VCC, is to introduce a current generator here instead of R. The standard way could be just use what the so-called current mirror, which is a combination of two transistors. I hope that you studied somewhere the current mirror. I know about people from Palermo, I'm not sure about other students. Or we can use a simplified version, that is this one. This is called the constant current Zener reference. Basic is a circuit using two transistors, Q2 and Q1, which has a feedback in the circuit, which tries to keep the current through the Zener diode as constant as possible. So we have VCC, a first transistor Q1, a load resistance R, a second transistor Q2, the Zener diode, and what is very important, this RSC resistance in series with the Zener diode. So we can try to study this circuit here and see how it works. The first approximation that we can do is to consider zero the base currents for the two transistors. Okay, so we can consider that the two transistors have zero base currents. We can have a second hypothesis. The second hypothesis is that obviously the circuit must work, is working. If the circuit is working, I suppose that all the transistors are in their active region. So the BJTs are in their active region. They are not saturated nor interdicted. This means that the base to emitter voltages of the two transistors are those 0.7 volts that we know. Okay, if the circuit works, I can say that for sure the VBL of transistor Q1 must be 0.7 volts. 0.7, 0.7 volts, okay? There is no base current, it's very small. So this 0.7 volts must come from the RSC resistance. But the RSC resistance has the same current as the Zener diode current. So when I say IZ, this IZ current goes through the Zener diode and through the RSC. So I'm supposing that this value of IZ times RSC gives 0.7 volts. Okay, if this is true, I can say that the VREF, the output of VREF, is given by the current, the voltage across RSC, that is, I can see from the formula, IZ RSC, plus the voltage drop across the Zener diode, that is, as we saw before, VBZ plus IZ ZZ. Okay? All those three terms are giving the output voltage. Well, I can also say that it is equal to VBZ plus IZ ZZ plus the voltage across RSC is 0.7, VBQ1 must be 0.7. Okay, so that's the formula if the circuit works. Now what I can try to see is if the system is able to keep a constant current to the Zener diode. One way to think about this simple way is this. Let's suppose that we found a situation for, let's say, VCC equal 10 volts. Then, for instance, we increase the VCC to 15 volts. What we could expect is that if we increase the voltage, there will be an increase in all the currents in the circuit. That's natural. When we increase the voltage, usually the current will increase. So I expect that the current through transistor Q2 will increase, but the current through transistor Q2, if there is no output current from VREF, is the same as IZ. So if I suppose that the current through transistor Q2 will increase, the IZ will increase, but also the voltage across RSC will increase. If this voltage increases, we are increasing the base emitter voltage of transistor Q1. This transistor will have a higher base current. It's always small, but will be increased. The base current will be increased. So the collector current of Q1 will increase. If the collector current of Q1 will increase, also the current through resistor R will increase. I can say this is this one is IC collector current of transistor 1, IC1, and is the same through R and the collector Q1. If the current through the resistor is increased, there will be an increase in the voltage across R. So there will be a reduction in the voltage on the base of Q2. A reduction in the voltage of the base of Q2 will reduce the current through Q2. Basically, the system will stabilize again when the voltage across RSC is more or less the voltage that we had before. Okay? So, again, maybe in a faster way. If we increase the VCC, the system will increase the current through Q2. But this will increase the current and the voltage across RSC, will increase the collector current of a transistor Q1, and so the collector and the base voltage of transistor Q2 will decrease. Decreasing this voltage will decrease the current through Q2 in order to stabilize the current across the resistance RSC. We can more or less say that the IZ will be quite stable and equal to 0.7 volts, that is the VB at Q1, divided by RSC. So if you want to design the value of the IZ, we can use this formula here. It's a very good approximation. Then one of these days, I will try to do with you some simulation. We'll simulate how stable is the circuit and see how it changes. Okay. So if we do this, the current through IZ is stable, and we know that if the current through IZ is stable, the output voltage is stable. That was basically what we saw when we studied this part here, the sensitivity to VCC. In this circuit here, if we increase the VCC, the current would increase, and so the output voltage will increase. In the other, in the constant current circuit instead, even if we increase the VCC voltage, the current is not increasing through the diode, and so the output voltage is stable because the VBZ plus ZZ is stable. Okay. There is a problem, however, with the temperature coefficient. Why? Because the output voltage VREF is given by the sum of something else plus the VB of Q1. And we remember that the Q1 has a negative time coefficient that is minus 2.2 millivolts per Celsius Celsius. So if we don't do anything, when the temperature increases, VB will decrease and VREF will decrease. But if we choose a Zener diode of 6.2 volts, we know that the VBZ has a plus 2.2 volts voltage variation with temperature. So in this case, what happens is that if the temperature changes, there will be an increase of VZ, which is compensating the decrease of VB. And so the output will be stable. The term IZ, ZZ, is stable because we have already stabilized IZ. So this is not going to change. This is interesting because with this circuit here, we have stabilized the output voltage in terms of VCC. In terms of temperature, we choose 6.2 volts for the Zener diode. And if we don't take current from the reference, it's stable also in terms of current. The only price that we have to pay is that actually we must have a voltage reference of 0.7 plus 6.2 is more or less 7 volts. We are blocked at this value. So we can have a stable circuit only if we take 7 volts from the output. If you want a different voltage, it will not be, again, stable with temperature. Okay, so this circuit is just a big improvement if we compare with the simple Zener diode, but gives an output voltage which is a bit too high. It's a bit too high if we think that the modern devices are working with 3 volts, 1.8 volts. So we cannot use this kind of circuit with modern cell phones and things like this. We must move to a different circuit. This is a very popular circuit which is called the bang-up reference. But we don't have time to deal with it today, so we'll discuss it tomorrow, okay? Cosa? Not those ones, only the one from the day before, okay? I have to check them again and then we'll load, okay? Okay, I'll try to do it. Should be okay. Okay. So, sorry for the many delays, but I think that now we can stop the presentation. It's around 2 o'clock, I think. Yes, it's 2 o'clock. So, see you tomorrow morning, okay? Bye-bye.
Bye. Bye.
Bye.
Bye, see you later.
Bye, Professor.
Bye. Bye. See you tomorrow.